Okay, thank you, Shantan, Raghunath, and other organizers for inviting. I think it was Gandhinagar where I was giving a talk, and Shantan asked some question to me, and in answer I said something. And he said, we are going to organize a event at IMSC roughly a year later. Can you give, no, can you talk about something around this word which I am avoiding? And I naively agreed, I mean, without thinking much. So I'm going to be talking about something in which I'm not an expert. Okay, I haven't really don't have an expertise on this, but I had committed, so I have to deliver something, which unfortunately means that if you have a great or even semi-great question, I would not be able to answer. Okay, because I don't have that perspective, but I'll try to nevertheless give you a glimpse of the field, and I'll soon tell you what it is about. How many of you are working in QCD? Everyone? Okay, almost everyone. Okay. So typically the story goes like this. You have a physical observable that you want to calculate, and you set up your action and set up a perturbation series. Okay, so I'm thinking of QCD right now. You could imagine the same thing for QED. So you have some observable in mind. Okay, it could be a total cross section or a differential cross section or anything like that. And okay, so imagine we are doing QCD and we want to, let's say, calculate total cross section for some observable. Okay, typically the result will be of this form. Let's say A is your observable, then you do a perturbation theory, you do your lowest order computation and get prediction for this observable to the lowest order, and then if you go one order higher in the strong coupling constant, you will get another term and so forth. Okay. Use the renormalization scale. Okay, that's what we typically do. So, or it could be a situation which is slightly more general. It could be some mth power of alpha s, because your leading order itself could have coupling constants there, some number here, something else. Okay, where the A tilde depends on the kinematics, the kinematical variables in your problem. Okay, so that's a typical situation, and the nomenclature is, if you have your lowest order result, you say I have a leading order result LO. If you have gone to the next order and included that in the sum, you say I have a next to leading order result, and if you go further, you say I have next to leading order result. Okay, and these calculations are extremely important for several reasons. Okay, so for example, for the story of Higgs boson discovery, it was extremely crucial to have higher order predictions. Okay, because if you had stopped at the lowest order prediction and then you had seen the signal in the machine LHC and tried to compare, you would find a difference of a factor of 2. Okay, it's a large gap, and then you might think, okay, I see something here, something being produced, but you would be concluding that that's something which you see is new physics signal, because the discrepancy is quite large from your prediction coming from theory, right? So that is why it's crucial to know your result as accurately as you can for observables, and especially if QCD is playing an important role, because strong coupling constant is not very small. Okay, so the corrections could be large. So that's typically what is done, and that's why we have lot of efforts being put in getting higher order computations. Otherwise, it's very easy to believe that what you see is a new physics signal, even though that was going to have matched with your prediction if you just worked a little bit more hard to get the higher order terms. So here I'm imagining something like total cross section. Okay. So as you calculate successive terms, your estimate gets better and better. Your deviations away from the true result, whatever that is, if you, let's say, could calculate it non-perturbatively, okay, the deviation away from the true result of this perturbative result becomes smaller and smaller, and that's why you are doing this. Okay. So what you do here is, you say, okay, I've calculated up to this term, the remaining I throw away. But when you say I'm throwing away, you are assuming that what has been thrown away is way smaller than what you have retained. Otherwise, throwing away doesn't make any sense. Okay, so that's something you could say for things which are like total cross-section. Let's say total cross-section for Higgs boson or anything else. Then you also have other kinds of observables which are like differential distributions. Okay, so again you do the same procedure. You go ahead and calculate things to fixed order in perturbation theory, but then you find that near certain kinematical regions, I'm thinking of now PT resummation, PT distribution. Okay, so think of this process. You are producing a Higgs boson in the final state. Okay, and you are looking at the transverse momentum of that Higgs boson in the final state. So you are looking at this distribution, or you could have 1 over pt square d sigma dpt square. So you calculate it to some accuracy. Okay, okay, and you can try to declare that this is my result. But what happens is, if you look at this result, these coefficients are actually containing logs of pt square. Okay, so when you want to know what's the distribution for low values of pt, and you are interested in that thing because the physical result will be very large in that region. Okay. When you are interested in that, you are in a region where you are asking a question about the observable where these coefficients are becoming large, and they become large very systematically. So a naive way of working where you throw away all higher order terms believing that they are small does not work, because these logs come with higher and higher powers at higher orders, and you cannot naively treat alpha s as your parameter of expansion. Okay, because it's coming with log with ever increasing power. Okay, but you can still save the situation by taking all those large logarithms and summing them up and getting a finite prediction. Okay, so for such distributions, again, you can get you can make a contact with the experiment by summing up all those large logarithms that appear at each order in perturbation theory, and that undergoes the name resummation. Okay, so PT resummation or soft law resummation, these kind of threshold resummation. And here the physics content is always like this. When you say I want to know the PT distribution at small values of PT, okay, the moment you ask this question, I want to calculate this, what you are doing is you are forcing all the radiation, the gluons and partons that they are emitted in the final state, you are forcing everything to be soft or collinear. By soft I mean low momentum. Collinear I mean the final state emissions are parallel to one of the hard partons. Okay, so when your question about what's when you want to know what is d sigma over dpt square at low values of pt, you are forcing the radiation, which is basically gluons and partons, let's say partons, in the final state to be soft. Okay, soft meaning their momenta is becoming small or collinear, and or depending on your observable. Okay, now that's an important point, because I am forcing these things to be, the radiation to be in this region, and I also know that the amplitudes diverge when you have soft emissions, right? The scattering amplitudes will give you, the amplitudes will give you divergent behavior if you have soft or collinear emissions, okay? And that is what shows as this large logs, right? So amplitudes are divergent in those limits, but your observable, your question itself is forcing them to be in that limit, and you get a divergent answer, okay? But the pattern in which that happens is universal, and that is why one is able to do resummation and get a prediction which is meaningful. So looks like all is good, and we could happily do perturbation theory and stop at some order. Now I'm going to do some calculation and show you something new if you have not seen it before, and that will bring us to what Shantan was asking me to tell about. Are there any questions up to this point?
So in the d sigma dpt square distribution, the hash that you wrote, so that has some other function of pt as well, right? Apart from log pt square, right? Or is
Please,
it a single?
let's go ahead.
Uh-huh.
You complete the question and then I can say.
So that's the question.
Okay. So what we are interested in is the behavior which is going to give you trouble, the divergent behavior, and that is coming purely from the logs. So you have logs to higher powers as you go to higher powers in alpha.
Okay, so there is a extra function that is sitting, but that is not a divergent behavior. That's what.
That is not the divergent behavior. Yes. So it will typically have 1 over pt square, these kind of things.
So let's say for the KLM theorem. So in the KLM theorem, we know that the divergence will cancel order by order, and so if I apply the same theorem for the physical observable, let's say here PT distributions, and if I demand that in every order it should cancel, and we should get some finite contributions.
Yes.
How do you see that actually?
Yeah. So that is what is happening. You get, as long as you are at any fixed value of PT, you have a finite result. You don't have any poles, right? These are, so some value of PT is there. You put that value, you'll get a prediction. The problem is that what you're throwing away, those dotted things, they are also large.
But they are in different order. But KLM theorem tells us that order by order they should cancel.
Different order is fine. So when you say different order, you have in mind an expansion parameter, which is alpha s in this case. Okay. But what if that is not the right parameter? So you are assuming, when you say that's the expansion parameter, or that's a certain order, your assumption is that the coefficients are not growing in a systematic form, which will invalidate you using this as a parameter. Okay, so that is what happens. So you have alpha times a log, which you should treat as a expansion parameter. You understand? Maybe I can show you some expressions later from my slides and it will be clear. But the point is this: you cannot treat alpha as the expansion parameter if the coefficients have this issue that at every order they are becoming more and more divergent in a very systematic way, and you cannot treat that.
Sir,
Yes, please.
what does collinear exactly correspond to?
So think of some process which has happened. Let's say you collided two protons, okay, and then in the final state you have, let's say a quark going or a gluon going. Okay, let's say a hard quark. By hard I mean it has a large momentum. Okay, so that quark is going in some direction, but as it goes, it also emits radiation. So it's emitting gluons, quarks. Okay, things are coming out. If these are parallel to the direction in which that quark was going, you say the radiation is collinear to that hard particle.
Then how it is correspond to this low PT thing which we are.
Yeah, so all I am telling you here is that if you take a final state in which a Higgs is produced, and you are saying what's this d sigma over dpt, where pt corresponds to the pt of Higgs, then the remaining radiation is going to be mostly collinear or soft. Okay, because you are looking at pt equal to 0. Your initial state didn't have a pt, transverse momentum, so the final state would also not have. Okay, the sum would be 0. Is that okay? Okay, if no more questions, then we can go ahead. So, the thing we keep in mind is we throw away things, assuming they are small. Okay. Now, I'll give you a observable, give you some results. I'm just taking from a review and giving the results. You can try to derive these things later. So this will be more like an exercise which I urge you to do. So consider a correlation function of two currents J mu is q bar gamma mu q, and these are massless quarks. Okay, the quarks are massless. So you are calculating the Fourier transform of this. That's the object we are interested in calculating, and you will be able to show that this is, you can write this as okay, of this form. So remember, when we do renormalization, we ensure that the amplitudes are finite. Okay, order by order, we arrange for them to be finite. But that doesn't mean that anything that you calculate in quantum field theory would be finite after you have done renormalization. Okay, you can have observables which will be still divergent even after renormalization. Okay, so here the function, it's called Adler function, which is defined as d of q square, and it is defined as the derivative of the coefficient here. Okay, now it turns out that this object, this Adler function, does not require any additional subtractions once you have done the renormalization of the Lagrangian. Is this statement clear? So point is, if usually when we are studying in our very early years in quantum field theory, we do renormalization and we see that things are finite, the amplitudes are finite. Okay, but it is not that everything is finite that you can compute in quantum field theory after you have done renormalization. So there could be quantities, and there are many quantities which are divergent, and I am giving an example of an object which does not require any additional renormalization after your original renormalization of the Lagrangian. Okay, so this is this object, Adler D function, and that's what I am interested in. It's of not much consequence what exactly that thing is. If you have not seen before, do not worry. The real thing is a little later. So some function, and this is this does not require any additional renormalization or any additional subtraction. So let's calculate this, and by this I mean I'll give you the result and you can later do it as an exercise. So we will have contributions of this form. So these are your currents, and let's look at the lowest order contribution coming at order alphas. Okay, so at each such vertex you have G, so that's alpha's contribution to that thing, okay, to D. And you will also have and other contributions. I'm going to focus only on these contributions. These are gauge invariant. You can check these contributions are gauge invariant, and there is something important I'm going to show that comes from this. Okay, so but then you could go and say, okay, no, why just this one? I can also, that's a fermion, okay, and this is Q. That's loop momentum K, and there's another loop momentum L flowing here. Okay, and you have to do integral over K and L to get your final thing. Now, let's say why only stop at this order? Let's see what will happen if you go to one order higher. So that's your fermion loop. That's a gluon. I take another fermion here. Okay, I will also take this contribution. And I can have multiple loops. Okay, put n of these, and there is K flowing here, and there is L flowing there, and similarly here. So my plan is to not just take the lowest order corrections, but rather include all these sets of diagrams. Okay, these are called bubble diagrams. So when I'm doing this, I'm actually not restricting to some fixed order in perturbation theory, because this number of bubbles, I'm going to let it be n, and then I want to know what happens as n is large. Okay? So what's the contribution from the nth term, where n could be 1000. Okay? That's the thing which we want to determine. So exercise, check that the renormalized fermion loop is given by that's the renormalization scale. I have renormalized the theory, so alpha s will be at mu square. This is what you will get. Okay, and since you are doing renormalization, meaning to this you have added a counter term. So when I'm writing that result, that counter term is already included. Okay, that's in here, and the finite piece depends on the scheme of subtraction, right? So when you do renormalization, how much finite quantity you subtract, it's your choice. So if you choose a MS bar scheme, you get -5/3 in MS bar scheme. Is this statement fine, that it's your choice how much you subtract? Sorry? That's just the bubble. Just this bubble. Okay. after renormalization. So
When you do the mass renormalization computation here, why do you only keep such diagrams? Why not? I mean, I'm just asking, like, why only these strings attached this way and that way? Why not?
yeah, so I should include everything that should be included at that order, but I choose to do this because that serves my purpose of showing you a peculiarity here. So yes, if
No, sorry, I didn't understand your answer. So, in principle, you should keep all 1PI, but for some reason, you're dropping some set of 1PIs and keeping a very special set where there are these necklaces and going this way and this way.
see, there are many things that you could do.
Exactly.
You could say, why just this? Why not this one also?
Exactly. So that's what I'm asking.
Right? Many of those things.
Yeah.
Yes, they are all there. But there's a point that I want to make, which you will see. For that, this is sufficient. So this is fine. The C will depend on the scheme. Okay, so finite amount, you can make it 0 if you wish. So I'll just tell what these other things are. Beta naught f is the contribution to beta function, beta 0 coming from the fermion loop, and that is the number of flavors T over 3 pi, where T is coming from group theory, T is half, and where beta alpha s and the notation is and I'll also give you the expression of beta naught non-abelian plus beta naught from the fermion, which is the thing here, and in this setup you have 4NF, number of flavors, T over 3, and your usual Ca is this, n is equal to 3, T is half, and NF is the number of massless cork flavors. Okay, so as he was asking, this is not all that you will have. You have many more diagrams here, but I choose to work with a special set because that is sufficient for me to show you behavior that I want to show you. So we take this, okay, and integrate over the loop momentum L, and also integrate over the angular variables corresponding to the loop momentum K. Okay, K flows in here. So I'll just draw it bigger. So this is K. Okay, the same K comes here. So what do we get? D, the Adler-D function, is of this form. So since I have all these insertions, bubble insertions, these are called bubble insertions which are of this form, okay, and at nth order I would have n of these, so there will be a power n to that, because after all, in each, the momentum that enters is still k, okay, it doesn't change when you go from one bubble to another bubble. The momentum that flows in is still k, and you get this. So I'm summing up over all bubbles from 0 to infinity, and you will get the following. This, what I'm writing here is this piece. K tilde square Q square over mu square plus C power n. And C is minus 5 over 3 in MS bar scheme. So what I want to do is keep mu fixed and then take it to be of the order of Q, okay, the momentum scale in the problem, okay, and then take and going to infinity limit, okay. So what I am essentially doing is taking the contributions of this infinitely long bubble chain, okay, which means I am trying to estimate the contribution coming at, if N is very large, contribution coming to my observable D from that nth order alpha to the n term, okay, which is including this bubble.
I got a bit confused, so I'm just clarifying. The Adler D you introduced as the derivative of the stuff in the the 2-point function of the current 2-point function, and so you're computing this D for this diagram. So should I be interpreting these bubbles that you're drawing without these external lines as the 2-point function of the current, those 2 points?
Yes.
I see. And so whatever answer you write down for the D, I just integrate it over the external Q squared to get the.
No, there is no external Q. This Q square you are not integrating over. You have to integrate over the loop momentum. The physical result depends on Q square. Okay, that's the physical thing in your problem. Okay. You have to do integral over loop momenta. So you have L and K as loop momenta in this case. So I'm going to show you the result after doing integral over L, D4L, and the angular parts of K. Okay, so that's the expression that I give. And some homework to do because I have.
And you should.
Yes.
And you should probably have had.
No, it's here. It's.
You should have had a number of many loop integrals, right? Because you're doing this arbitrary diagram. I'm just a bit. I mean, maybe I'm just not looking at the formula correctly. Where are the many loop integrals?
See, I've given you the expression of this.
Huh.
1. Where is it? It's here.
Oh, I see.
This depends only on K which enters. Mu is the renormalization scale.
Good.
And it's the same K which enters in each of those, so that it will be of that form. Okay?
Okay, this is just one final question before we go ahead. Like, what was the motivation for computing the current 2-point function again?
That's yet to come.
Okay.
Okay. So one of the reasons is it is you do not require any additional subtractions. So this object is finite. Okay. But as later you will see that this is a generic thing you will worry about in all observables once I have come to the conclusion part.
Anurag, so I didn't get then the log factor of K tilde square Q square. So you have K tilde is K by Q or?
Yeah, I should. Yeah, I was writing when there was a question. So where Q square is minus Q square and K tilde is K square. Okay, so angular integration has been done. The result will be of this form. You can check it in literature, how it comes about. What I'll do is, I'll tell you the behavior of F for small and large k. Okay, K tilde. So as you can see, the contribution to D on the right hand side has these bubbles, n of them, okay, each contributing this, so they are multiplied together. whatever remains is f, and that's the contribution of the big fermionic loop, right? This is f knows about this, that the information in f is this thing. Is that okay? Because the remaining things are just bubbles and they are sitting there. Yeah.
What about the gluon propagator in between the two bubble?
That's also taken into account here.
In the F K tilde.
In the f and over, so this part knows about 1 over k square you are worried about. Okay. Here these are the insertions, and of course you will have that propagator. It's all in here. Is that okay?
The Adler D, is it like a well-defined one mathematical function, or is it something that you define at every order for some? Okay, I'm just asking for nomenclature. Is it some like gamma function some D, or like is it something that you define at every loop order to be something?
I gave you the definition in the beginning, even before writing diagrams.
Yeah, as this.
This correlator, right?
As this d pi squared over.
That correlator I wrote as, it will have this form.
Right. Right.
Okay. The derivative of this thing is Adler-D function.
Okay.
But whatever I'm going to say, and the point I'm trying to make, does not depend so crucially on knowing that observable. Okay. So okay, so this is what we want to do.
Okay, sorry to keep harping on this, but
So I'm going to tell you how the subject behaves in small k limit and large k limit.
I am
Yeah.
so sorry, but so I mean you're computing this d for this set of diagrams, right? But I'm probably it's the same question as before, but these other contributions are also in d, but you're just taking this contribution to see some value.
That is correct. And the answer is like before, this will serve my purpose. Okay, and in a moment you will see. So there is a mystery about to unfold, and that's sufficient for that mystery. Okay, so let's look at the regions where k is much larger than q and k much smaller than q. Okay, these two regions I am interested in. So that's your infrared region. The loop momentum is much smaller than your scale in the problem. That's the ultraviolet region. The loop momentum is much larger than the scale in the problem. Okay, and again exercise. Once you start figuring out what d is, you can also take the limit, and I'll give you the references later. Show that this is of this form. Okay, for k tilde much smaller than 1, you are in the infrared region, and for k tilde much larger than 1, you are in the UV region. Okay, so that is the approximate behavior, and you can actually find also the exact result is also given in the literature, and there are corrections to this of this order. So you have k tilde to the 4, you are looking at k going to 0, so it's falling off as k tilde to the 4, and there is 1 over k square there. Okay, so the corrections are k tilde to the 4 times k tilde square log k tilde square. Okay, so this is suppressed compared to this one, and similarly here the corrections are of this form. So again it is this piece log k tilde square over k tilde square, that's here. It has further separation over of 1 over k tilde square, since you are looking at k tilde to be larger than 1. Okay, so that's the approximate behavior of the contribution coming to the Adler-D function from the big fermionic loop. Okay. So up to now what I have done is taken some object and inserted lots of bubble diagrams in it and trying to figure out what it looks like when the momentum flowing in that is either large or small. Okay, that's what I want to do. Did I erase something? Okay. So now I'll do some small algebra. So I'll split the integral at k tilde square is equal to mu square over q square e to the minus 5 over 3. Okay. So the choice is guided by this argument here. Okay. That c is minus 5 over 3. That's log of, sorry, e to the log of minus 5 over 3. So I'm using that thing to split the integral. Okay. So this guides the split, and you get the Adler-D function to be the following. And we are close. We are very close to seeing something nice. Actually, seeing something not nice. This is about something not nice. Okay. So you have your strong coupling constant. I am splitting the integral from 0 to this choice. So you have dk tilde square over k tilde square 2 pi. Then I have a k tilde to the 4, which I had written here earlier. Okay. And what you have is beta naught f alpha s of mu square log of k tilde square q square e to the minus 5 over 3 over mu square power n. Okay. So this thing is same as what you had here. Okay. With c being written as e to the log of minus 5 over 3. So that's this. That entire factor is raised to the power n. I have used the approximate result for f tilde in UV. Sorry, that is in IR. And then the remaining one is this. Okay, you can check that what you have in your note matches with what I am writing now. Q square e to the minus 5 over 3 over mu square power okay. So I'll give these two terms names. I'll call this one as DIR and this one as DUV.
Excuse me. So in the right hand side of the board, so this D you have written. So I don't understand why there is only one gluon propagator. Can you this?
There is only one?
So 1 upon k tilde square, only one. So shouldn't it be 1 upon k tilde square to the power n, something like, because there are n gluon propagator in n bubble diagrams?
Uh,
Okay.
okay, I can think about it. It will not come. I'll think. I'm not able to say immediately why. Okay, maybe for later.
Every bubble has 1 by k square, 1 by k square. The bubble also gives you k square. So that is how we could write a series as.
But I have actually already given the result for bubble.
No, bubble should contain some k square. Otherwise, dimensionally it's not correct. Dimensionally, if you look at one bubble, it is proportional to k square. It's minus g mu nu k square plus k mu k nu. That's what is multiplied from k to nu.
Most likely that will explain. Okay, that should be the answer. But we can check this later explicitly. Okay, now we are very close to seeing something very bad. So I'll actually, if you do that sum, if you look at the entire 2-point function, you will get something like 1 over k square times 1 over 1 plus this bubble. Okay, when you do the entire summation, and it is this thing which is when you are expanding 1 over 1 plus x, right, as 1, or let's say 1 over 1 minus x as 1 plus x square. This is this thing here, those powers. Okay, so it's really 1 over k square, but we can check explicitly how it comes. But when you look at the 2-point function, it still has 1 over k square only. Okay, 1 over k square times 1 over 1 plus that 1 pi. So define A equal to, so I'm sorry for the notation, this A has nothing to do with the A I wrote in the first few minutes of the lecture, observable. Is some factors here, okay, and I'm just doing a change of variable, or k tilde square is z over A, and as k tilde square goes to 1 over A, z goes to 1. Okay, it is just to make the integral from 0 to 1 and 1 to infinity. That's all I am doing. Okay, and I want to do these trivial steps because then there will be no mystery about the thing that you are going to see. So D1 or DIR is this thing. It involves 3CF over 2 pi. No, not involves, it's everything. Summation alpha s integral 0 to 1. After doing the substitution here, you get dz over a, z over a, beta naught f alpha s log z to the n. Do you agree to this? This is it. So I have actually chosen variables so that this becomes 1. So it becomes 0 to 1 dz over a. This k tilde square cancels, k tilde to the 4 gives you k tilde square, and that is 1 over a, that should have been z over a. Gives you z over a, so that is that z over a, and this is beta naught alpha s times log of z, that is z. I have not done anything special, just change of variables.
Yeah, so I was asking like I was asking like, so there are intermediate gluon propagator, and you said that that is being taken care by this F. So, it's also related to the verbal question. So, when you write, let's say in the infrared region k tilde to the power 4, how do I see that from let's say from the infinite when you are taking the
So
series?
the best strategy right now would be take it as an exercise, figure out that this is correct. If not, let me know, because this is what is going to come out and we can discuss about this after this lecture, okay? So maybe I'll proceed because that I have already answered. We will proceed with this. Okay, so that's DIR, D, one part of the D in the infrared. So what you eventually have is here in this, maybe I'll write it neatly. So up to here it was all fine. Now I am left with one integral here. It's from 0 to 1 dz z log z. I think there is a mistake here. Yeah. Log zn. If you agree to this, that after change of variables, this first term in the D is this, then we are in a good situation. So there is some integral which eventually comes about. It is integral 0 to 1 z log z to the n. Okay. Okay, now one more step away from, how am I doing with time? It's 20. Sorry? Okay, so let's see what we can do. I was about to leave it as an exercise, but since I have 20 minutes, I will just do this integral because it's easy and I can do it. So let's look at this integral I. Okay, I'll do integration by parts. So that's my first function, second function. So I'm writing as I tilde evaluated at these limits 0 to 1. Okay, and when I do integration by parts, you can check, even while I'm writing, you can check that this is what I get. So that's the first function. Then the integral of this, that's z square over 2 minus derivative of integral, derivative of first function. So it reduces the power of n by 1. And then because log z will give you 1 over z, that's here. And then this still gives z square, right? Because that's the integral of that one. So you get this, and this gives you a recursion relation, which is log z to the n z square over 2 minus n over 2, I pull that 2 out, integral dz z log z to the n minus 1. So you have a nice recursion relation now for okay, now you can use this repeatedly to evaluate this. So every time you use integration by parts, the power of log will get reduced by 1 and eventually you go to the power 0 and then you have the result. So let's do that. So I will write it as, maybe I'll write here, in 2 lines, and then we are done with, and we'll be having our final result. So I'll rewrite this recursion relation slightly differently. I mean, just rearrange terms. dz, z to log z to the n is what? Minus n over 2, that's the second term which I am writing first. Sorry, small n. Okay, and then I use this recursively. So I have n minus 1 this time, so I'll have minus n minus 1 over 2 integral dz, z to the log z n minus 2, and then this kind of term plus z square over 2 log z to the n minus 1. Okay, so I have used recursion relation for rewriting this term here as this, and that term is still there. Okay, so that's what we have. Now you can again do this repeatedly. So you see what you will start generating is n over 2 minus n over 2, sorry, n minus 1 over 2, n minus 2 over 2, and so forth. Okay, put the limits and check that I think the behavior is already visible. So you supply one line and you'll get the following. So n minus 1, n minus 2, and so forth, that will give you n factorial. Then you have minus half from each of these. So that's minus half to the n, and at the end you will also have one half you will get. Okay, so I have it in my notes, I am not showing it, it's easy. This is what you are going to get. After I have made my comment, you can make yours. Otherwise, my fun will be gone. Maybe you steal my fun. My thunder, yeah. Let's go back to the first few minutes of this lecture. I was saying we do perturbation theory, and we keep first few terms and say, oh, my prediction is getting better and better as I keep including more terms. Okay. When you say that, you have in mind a convergent series, because what you are throwing away, you assume it to be small. But now what I have shown you is that because of this, now you see this is the thing sitting in here, right? This is what I had written as dir, and this integral was converted to the integral over z, and that I have evaluated, and it is giving me n factorial here, right? So the coefficients which come with alpha s to the n, they are not coming down. You are not seeing a convergent series. What you see is a series which is divergent factorially. Is that okay? You like the bad news? That's your bad news. Okay, the entire effort was to show you that whatever I said in the beginning, which appeared nice, actually something else is missing. So it's not clear what we are doing then. I mean, what's the point of then even calculating anything? If after all you could muster courage and go to 10th order and 100th order, things start becoming bigger and bigger. So what is your prediction after all? It seems like there is no prediction. Is this one? Before your comment, someone else was waiting for a comment.
I mean, my comment is probably, maybe they should go ahead, I'll say.
Hello. So my comment is like you are making this assumption on the basis of this kind of only looped bubble loop diagrams, right? So there could be a diagram at each order which can compensate this part. So we cannot say this statement, right?
Yeah, but that will be an amazing conspiracy there. that will cancel. There is nothing special about these ones. See, usually those kind of cancellations happen because of certain symmetries.
Yeah.
Okay, it's not evident that there is something of that sort is going to happen, and it does not happen. So no conspiracy is going to help you with this.
So I have the same question actually related to this. So by picking up certain set of diagrams, we may violate the gauge invariance, and the conspiracy come from there actually. May come.
No,
How do you justify this that in the soft limit or IR limit this is the structure?
So it is not those issues which are at stake. The thing is, you have actually diagrams which give you factorial growth. Okay, so gauge invariance is not going to save you, and the diagrams I started with, they are gauge invariant. So that set which I took is actually gauge invariant. That's why I took that. You remember the bubble with a cross line of this fermionic loop with a bubble line here, and then two others, that forms a gauge invariant set. So it is not the gauge invariance which is behind all this. It's just you have a factorial growth coming from these kind of diagrams, and these are not the only source of diagrams which give factorial growth.
That set, when you are considering at let's say 2 loop level, how do I know that when I increase the loop more, that set will be intact? So how do you check the, let's say, let's put in this, how do you check the gauge invariance?
As I've said, it's not a field in which I have worked, so I will not be able to immediately answer that. But the upshot is, this has nothing to do with gauge invariance. Okay, this is a behavior coming from these kind of diagrams. It's not the gauge invariance which I am violating because of which this is happening. It's not that. Okay, but I can direct you to the literature, and you can try to find out.
Can I ask? So this point that you're making that everything is divergent. After all,
Sorry, say again.
the point of the divergence. After all, everything that we write down in quantum field theory is a perturbation expansion, which are asymptotic expansions, and they're all divergent. For example, you take QED and compute a 137th loop diagram. Most people would say but probably you'll start seeing things going away from perturbation theory. So here is the statement that I can't even do like a 3-loop computation and give an answer at 3-loop itself. It goes wrong. Like, what goes wrong? Where will I start seeing things going wrong had I not done this general analysis with arbitrary n?
Okay, so that is next lecture. Okay, I was told that these are I have to give lectures to first year students. This is what I understood. So I'm assuming that most of the audience is not aware of it, but you are right. That is where we are headed to. Okay, that is the question.
And the comment was just about the integral. I mean, I was just going to say that you put log z equal to zeta and just trivially do the integral recursion. The integral, the recursion seems like overkill, right? You just put log z equal to zeta and then just trivially do the integral. You'll get that minus zeta.
Maybe that is what I was doing. Maybe it's not the nicest or fastest way. Okay. So I will give you one exercise. So finally, if you substitute it in here, the D, okay, anyway, you look up, right? So no problem. So D, you can check that it is okay. So I've just substituted what is Z in there, and that's the n factorial, the factorial growth you see, and then the second term okay, that is what our result is for the D function, including all those bubble diagrams. And as you can check, so you might want to know what's the radius of convergence for this series. So do you evaluate that, take the ratio of nth coefficient to n plus 1th coefficient and take limit n goes to infinity. Okay, so you find the radius of convergence. and you will find, what do you expect? 0. There is no value of alpha s for which the series is convergent, no matter how small. Okay. So irrespective of your choice of alpha s, you have this trouble, you have factorial growth, and stopping at any order in perturbation theory, whenever you stop, you are throwing away infinite terms, and we might then wonder what's the meaning of doing any calculation and giving a result. I think that will be a nice place to stop. Okay, maybe in the next lecture, we'll try to figure out what it means to do perturbation theory and what it means to say, this is my prediction for the total cross section, and go and match with the experiment. Okay, why that is not a meaningless statement in light of this, because these kind of diagrams you'll have everywhere. Okay, and you see that this problem will arise. So we will start looking into that in the next lecture.